Welcome back, students, to Unit 8, Chemistry, Thermochemistry, and Gases. Today, we will be talking about Unit 8.4, Physical Changes. From the top of your head to the edge of our thermosphere, there is 14 pounds of air pushing down on you at all times. That air pushing down on you exerts a pressure. As those air molecules collide with your body, they exert a force for each area of your body. This is what we know as pressure. We've known about air pressure since the Renaissance. Torricelli was an Italian physicist and mathematician that used air pressure to show how it changes at different elevations by the development of a barometer. He took a graduated cylinder full of mercury, flipped it over in a bowl, and the mercury came out of the graduated cylinder to a point because as the air pressure pushed down on it, it kept the mercury at 760 millimeters. So 760 millimeters of mercury is our first unit of pressure. At sea level, there's enough air pushing down on your body and the world around you to keep mercury 760 millimeters up a graduated cylinder. If you were to travel further up in elevation to the top of a cliff or to the top of Everest, there's less air pushing down on you, so that mercury would probably only go up 740 millimeters on top of a cliff, or on the top of Everest, 226 millimeters of mercury, because at higher elevations, there's less air pushing down on you. Torricelli's barometer we still use today. If you watch the news and they talk about barometric pressure, it's measured much the same way. We just no longer use mercury as it's a carcinogen. So in the early 19th century, we renamed a millimeter of mercury a torr after Torricelli and his experiment. So right now, if you are next to an ocean, you are experiencing 760 millimeters of mercury or 760 torr worth of pressure. During the Renaissance, science was founded based off the idea that all things are made up of stuff. So air was made up of different parts of air, and the earth was made up of different parts of earth. The idea that something could not exist didn't make any sense. So when Torricelli made his barometer and this empty space came out of it, this kind of led to a whole new idea in science. This idea of a vacuum was actually pioneered by Pascal, the French mathematician. He replicated Torricelli's experiments and was particularly interested in a vacuum because it shouldn't have existed at the time. Pascal found that you could use the air around you to do work, to exert some force for each area. A Newton for every square meter is what he measured the atmospheric pressure around us in. However, his experiments became so popular that we renamed a Newton for every square meter a Pascal after him. A Pascal is actually very small. If you were to hold a dollar bill in your hand, that dollar bill is exerting approximately 1 Pascal worth of pressure, or is exerting 1 Pascal, 1 Newton for every square meter on your hand. So that's, again, not a lot. If you are at sea level, you're experiencing 101,300 pascals, which has lots of decimal places in it. So we use the metric system and simply called this atmospheric pressure 101.3 kilopascals. So now we have 3 different units for pressure. If you're next to the ocean, you're experiencing 101.3 kilopascals. It could also be expressed in torr or millimeters of mercury. This led to a lot of confusion when reading scientific papers dealing with gases. Were their pressures in kilopascals, millimeters of mercury, or torr? Led to drastically different numbers. So, in the 1950s, the Conference of General Measurements got together and came up with a new unit of pressure that everyone could agree to, the atmosphere. If you're next to the ocean, you're experiencing 1 atmosphere of Earth. You can think of it kind of like G's, gravities, right? So if you're on Earth, you're experiencing 1 G. On the moon, you experience 1/6 of a G. If you get blasted off into space, you experience 10 G's, 10 times the gravity of Earth. You can think of atmospheres somewhat like that. Next to the ocean, you're at 1 atmosphere. On the top of Everest, you're at about 1/3 of an atmosphere. There's less pushing down on you. So now we have 4 units for pressure. Most of the time in this class we will focus on atmospheres, as it is the most commonly accepted unit of pressure. However, if we need our air to do work of some sort, we'll use kilopascals. Or if we are working with air or we want to express it in some older measurements, we might use millimeters of mercury or torr. There is a 5th unit of pressure that you will not be asked on the SOL, nor will you ever be asked about it in the class, but you might hear about it in the news, a bar. A bar is a atmospheric unit of pressure. It is exclusive to meteorology. A bar is approximately the same as an atmosphere. One atmosphere is 1.013 bars effectively, but then again, this is used exclusively in meteorology and is not even a recognized unit of pressure in most systems. So again, we will focus on the 4 units of pressure. Unfortunately, you do need to know all 4. You need to be able to convert between them. So example 4 in your packet has us convert between our units of pressure. At the bottom of the Marianas Trench, since you have an entire ocean pushing down on you, the pressure down there is 1,600 pounds for every square inch. That would be 1.1 times 10 to the 5th kilopascals. If you wanted that value in atmospheres to give you an idea of how much more pressure it is than what you're experiencing right now, you could set up your factor label method. If I want to get rid of kilopascals has to go into the denominator, and atmospheres can go in the numerator, and I can use the conversion between kilopascals and atmospheres. For every 1 atmosphere, there are 101.3 kilopascals. Kilopascals cancel out, and I get 1,086 atmospheres. So there's 1,086 times more pressure at the bottom of the Marianas Trench. Or if we go the other direction, let's say you were to step outside of an airplane at its cruising altitude of 30,000 feet. At that elevation, there's only 226 millimeters of mercury, so there's significantly less air pushing down on you, so there's only 226 millimeters of mercury worth of pressure. What is this in torr? You could set up the factor label method between torr and millimeters of mercury. However, since they are the same magnitude, they actually are the same number. 226 millimeters of mercury would be 226 torr. But if you wanted to convert that to, say, pascals, that's a little bit larger of a conversion. In order to go from millimeters of mercury to pascals, we first have to go through kilopascals. So for every 101.3 kilopascals, there's 760 millimeters of mercury. That will change us over to kilopascals, but if we want singular pascals, we would have to multiply by 1,000, because there are 1,000 pascals in every 1 kilopascal, which means we would have 30,123 pascals worth of pressure around us and in our airplane. That's enough to give you your first 2 note quiz questions. Pause the video and do note quiz questions 1 and 2 for Unit 8.4. The pressure around you can literally compress gas. We use a piston to compress carbon dioxide. As we put pressure on carbon dioxide, the electron cloud of carbon dioxide bunches up on one side or another, causing one side to be negative and one side to be positive. Those London dispersion forces actually allow carbon dioxide to form a solid. This is how dry ice forms. So pressure can actually cause a change in states of matter. So putting pressure under something can cause it to shift to become a more condensed state of matter. Removing that pressure will cause it to become a less ordered state of matter. This is because molecules on the surface of any substance are only attracted to the molecules below them. So that's a much weaker attraction than the molecules within the substance. So along the surface of anything, there are a few molecules that form a gas or vapor. That vapor exerts a pressure of its own along the surface of a liquid. Think of it sort of like these molecules are escaping. However, the atmosphere around them pushes them back down and keeps them in a particular state of matter. So in this case, a liquid. If you were to weaken the atmospheric pressure, so much so that it no longer can hold those molecules down, that's when a substance boils. A substance boils when its atmospheric pressure is less than its vapor pressure. The force at which it escapes exceeds the force pushing it back down. That's when a substance boils. This is why if you take your helmet off in space, every liquid within your body turns into a gas. Since there's no vapor, since there's no atmospheric pressure, the vapor pressure of the liquids within your body drastically exceeds the pressure around you, and so you basically fart out of every pore. So here are your next 2 note quiz questions. Pause the video and do note quiz questions 3 and 4. Example 5 in our packet has a vapor pressure versus temperature graph, a vapor pressure graph. On any vapor pressure graph, at some point the vapor pressure will exceed atmospheric pressure. So if you're at 760 millimeters of mercury next to the ocean, when these substances exceed that pressure, when their vapor pressure exceeds atmospheric pressure, this is when they boil. This is their boiling point. So you could follow those down. So this is the boiling point of mercury, the boiling point of water, and the boiling point of ether. Boiling points directly relate to intermolecular forces. So since mercury has the highest boiling point, it must have the strongest intermolecular forces, the strongest attraction between its molecules. Since ether has the lowest boiling point, it must have the weakest intermolecular forces. So to drive this point home, we did page 39 in the packet. Use your knowledge of atmospheric pressure and the graph on page 39 to answer the next 5 questions, as well as note quiz question 5, 6, and 7. Pause the video and complete page 39 and note quizzes 5 through 7. If you were to graph the state of matter of something as its temperature and pressure changes at low temperatures and high pressures, the molecules are moving very slowly because they have low temperatures, and there's a lot of force pushing them together, so their intermolecular forces build up. So you end up with a solid. When something is very hot, their molecules move extremely fast, not allowing their attractions to build up, and with no pressure pushing them together, you form a gas. And somewhere between the two is a liquid. This leads to what's known as a phase change diagram. Phase change diagrams I commonly refer to as martini diagrams because, like a martini, the liquid is in the middle. And it always goes solid, liquid, gas, the liquid being in the middle. Along a phase change diagram, you'll see some lines. Those lines show the pressure and temperature at which a substance goes through a phase change. So here we find the melting point at a particular pressure and temperature. Or here we would find the boiling point as this substance for this substance at a particular pressure and temperature. Or here we would find the sublimation point for this solid as it turns into a gas. There are a couple points to note on this diagram. The liquid line separating liquids from gases, the boiling points, does come to an end. This is known as the critical point. It's the point at which temperature and pressure no longer allow for a liquid to exist. You form another state of matter. So you know of solids, liquids, and gases. However, there are other states of matter, and one of them is a supercritical fluid. No one will ever ask you about supercritical fluid. They might not even ask you, hey, why does this line end? Just know that's known as the critical point. The triple point is where all three lines meet. At this point, you find all three states of matter. It would be like a cup of ice water that was boiling at the same time. So the triple point is where all three states of matter exist. With that, we are now done with 8.4. You can finish your note quiz questions 8, 9, and 10, and I will see you next time when we talk about the kinetic molecular theory and begin our gas laws.